One is a 2 by 2 matrix. So if you take a 2 by 2 matrix, it has 3 components, but at the same time, we know that it is stressless. So we are going to have only scalar and vector perturbations, which are the only 2 perturbations that we have for black holes in 4 dimensions. This is completely different than what we have in cosmology, where we have scalar, vector, and tensor perturbations. Here we are going to have only scalar and vector perturbations. People in the literature, they call them also odd and even perturbations. There are different names, but at the end of the day, this is the scalar and the vector perturbations. If you work in higher dimensions, like for example, if you work in 5 dimensions, you will have scalars, vectors, and here you will have a 3 by 3 matrix. 3 by 3, it's symmetric, it has 6 components. -1 for the trace, -3 for that. So we are left with 2 degrees of freedom. So then you have tensors. Okay, so we have only scalars and vectors. Now, because of the symmetry of the background, we are going to decompose each function we have. Originally, we have functions, which are functions of time and space, r, theta, phi. Of course, we use spherical coordinates because of the symmetry of the problem. Usually what we can do is just expand this into spherical harmonics. So we can always write this as a summation of some functions, f, which depends on L and M, which depends on TR, and the spherical harmonics. So we have something like that. So we could do that for all functions, but actually we can do it only for scalar functions. Yes?
Is this a unique decomposition for spherical symmetrical?
It's not unique. We can do any decomposition. Why it is nice is because at the linear order, these 2 perturbations, they separate. They don't mix. It's the only reason why we do it. Exactly like for cosmology. We had scalar, vector, tensor perturbations, and then these perturbations, they separate. And we get an equation for scalar perturbations, equation for vector, and an equation for tensor. Here, the same thing will happen because of this decomposition. You can do any decomposition you want. You are free to do that, except that all the things will be mixed, actually. And we get a very complicated equation. So if you want to diagonalize the degrees of freedom, separate the degrees of freedom, this is the way to do it. And then it simplifies your life. So for scalar actual functions, you can always define it with spherical harmonics. But for vectors, there is another thing that very often we don't use, but they exist. There exist also vector spherical harmonics, tensor spherical harmonics, etc. So you have also vector spherical harmonics. What is a vector spherical harmonic? It's some spherical harmonic which has an index, actually. And it is more or less some Levi-Civita tensor times the derivative of the spherical harmonic. This thing, epsilon ij, is just the square root of the matrix. So what does it mean? That epsilon theta phi is equal to sine theta, epsilon phi theta is minus sine theta, and if there are 2 which are equal, then it's 0. This is the Levi-Civita tensor, but in curved space-time, so it's not equal to 1, but to the square root of the determinant. And but it has the same thing. It's completely antisymmetric. We work only in 4 dimensions, so this subspace is 2-dimensional. So we have only these 2 indices. Otherwise, it might become a bit more. But this is for vector perturbations. There exist also tensor, spherical harmonics, etc. But in 4 dimensions, they don't exist, so we don't care about them. So we have only 2 types of perturbations, scalar, vector perturbations. Any scalar, we will decompose it in this way. Any vector, we will decompose it in this basis, actually. And with that, we are fine and we can do all the calculations. So if you focus first, for example, on vector perturbations, which is the simplest thing, vector perturbations, sorry.
Explain this decomposition, the 7 scalars and...
Yes. So as we said, first of all, we separate each component on how they transform under rotation. Rotation under the angle theta and phi. This one doesn't change because it's dt squared, so there is no rotation at all. So these are scalars, these are vectors, this is a tensor. But now, thanks to that decomposition, type of Helmholtz decomposition, the Hodge decomposition, we know that a vector can be written as a kind of a pure vector, divergence-free, plus the gradient of a scalar. So this one has a scalar here. Actually, it's a derivative of a scalar. This one has also a derivative of a scalar. These two vectors, they bring each one scalar more. Okay? So each vector here, which is a two vector, it has just two components. Each vector can be written as some sort of special vector plus the derivative of a scalar. This means that the gradient of it is actually 0. So we decompose the vector, which is originally, it has two components, into something which is one scalar, which is some sort of combination of this, plus one vector, but which has this constraint, so it has only 1 degree of freedom. So this one has 1 degree of freedom, and this scalar has 1 degree of freedom. So we just decompose the two into 1 plus 1. Okay? A vector with this constraint has 1 degree of freedom, and the scalar, it's just one number, it's 1 degree of freedom. So each vector has one scalar. So we have 3 scalars here, is the 3. Each vector here has a scalar, so we have 2 scalars more. And then there is this tensor here. This tensor, we saw that actually it can be decomposed in the same way that we decompose it in this way. It can be decomposed into something like that. This is the Hodge decomposition into some pure tensor, some gradient of vectors, plus some trace, and plus actually the full derivative of this object. So then we have 2 more scalars which appear in that decomposition again. We don't lose any degree of freedom, we just separate things. This is a 2 by 2 matrix. 2 by 2 matrix means that it has 3 components which are independent. Where are these 3 components? One is here in phi, one is in psi, there are 2, and one is in this vector because it's a 2 vector, but with a constraint, so there is only one which is independent. And this one has nothing, so it just disappears. So we have 2 scalars more coming from this part here. So a total of 7 scalars. So at the end, we don't lose anything. We have really 10 degrees of freedom, as it should be for a 4 by 4 matrix. And we just made a decomposition, a separation into scalar vectors and tensors, but the tensors, they don't contribute in 4 dimensions. And then we do a decomposition, each scalar into spherical harmonics, each vector into vector spherical harmonics. And with that, we are fine. We can separate the two perturbations. So let me just do it for vector perturbations, and then you have it in the notes for the scalar perturbations. So we said the following, is that we have this. So I'm focusing only on vector perturbations. I have one vector here. I have another vector here, and I have this vector xi, which is here. So I have 3 vectors. And each vector, I will decompose it into the vector spherical harmonics. So I don't know, we'll call it some SILM of theta phi multiplied by some function f, let's say, of tr. Okay. So that will be a decomposition in the basis of vectors which are the vector spherical harmonics. So I can do that, and the vector spherical harmonics are defined here with this Levi-Civita tensor. Okay, so let me just write maybe one or two as examples to see how it works. Let us take this one here. The term here, I will focus on the first term here. I think this is the one, for example, I did, yeah. H0, ht theta. Let's write it like this. So this is this term here, the time, and the third component, which is theta. So this is initially a vector. Let's just see the notation I used. So the notation I used is the following. H0a is the summation. On the function I call it HLM. So this is the decomposition into the basis of vector spherical harmonics. So ht theta will be what? Will be the summation over the values of L and M. You know how it works. The M goes from minus L to L, and L goes from 0 to infinity, as usual for spherical harmonics. So you do this decomposition, you get something here, some function, whatever function it is, and this term here is the S theta Lm theta phi. So now what is this S theta? I'm just using this formula here. I'm having this thing here. So it's epsilon theta j dj of a spherical harmonics. Now, this index, they cannot be equal because it's a complete antisymmetric tensor. So j can take only the value phi. So it's equal to epsilon theta phi d phi yln. So this is what I have. Now, what is this Levi-Civita tensor? I have to reduce actually one to lower this index. So this thing here is just gamma phi phi. Gamma is, as we said, the metric in just the sphere. Epsilon theta phi. The gamma phi phi is equal to 1 over sine squared of phi, and the epsilon theta phi is equal to sine phi. So it's 1 over sine phi. So we are left with something which is the summation Lm, some function 1 over sine phi, the derivative of phi, spherical harmonic. So this is going to be the ht theta. The term here, I will write it like this. I know what are the spherical harmonics. This I can calculate it easily. This is going to be my unknown object that I would like to calculate through perturbations. And just and then, just by definition, this one, the people for simplicity, because it simplifies the calculations, they introduce a minus sign. So the h theta, t theta, we call it minus h0. Okay, so this is what we have. I don't know if it is clear. If you want a second example, I can continue. Answer. Second example, or okay, so I just continue. Okay, so you have then this this metric. The components here, you can write them all in this way. So you do it for all vectors. And you will introduce, actually, we said that there are three vectors, 3 degrees of freedom. So you will get 3 functions. One is this function h0tr, another one is h1tr, and the third one is h2tr. So then you just write actually your metric. Let me write it. So if you write h mu for vector perturbations, so this is what we are doing only. So what is h mu? For vector perturbations, the first on the top, they are scalars. So scalars, they don't contribute to vector perturbations. So they are just 0. These terms will appear in the case of scalar perturbations. So they are not there. This one, we just wrote it here. I will just remove the summation to make it simpler in terms of notation. This one will be an h0 sine theta d theta. Everything applied on the spherical harmonic. So then you can write them all and you get this. The diagonal term is a bit actually I don't have to write it. You have the notes, page 62 actually it is. Okay, so you will get something, some object here on the page 62, and you find the full h mu, which is the perturbation for vector, for the metric for vector perturbations. You can do the same thing for scalar perturbations. Now you decompose into spherical harmonics, not vector spherical harmonics, and you will get the form of it. So up to here, we just made actually a decomposition of our metric.
So here means you are choosing your h t theta and xi, no? You are taking that.
No, I'm not choosing it yet.
Yeah, you are not, but the form of hi theta. So the left hand side h t theta, sorry.
Ah, this one? No, I calculate them all. I know that this is a scalar, so I don't have to calculate them because I'm looking to vector perturbations. But then I look to ht theta, it gives me something. Then I go to ht phi, and it gives me something else, which is this one. Then I do hr theta, hr phi, etc., etc. And I calculate them all one by one, and I'm getting each one here.
No, but then how is that this formula, this h t theta is equal to?
Yes.
Yeah.
This, because one is that I know it's a vector, according to the decomposition we did. Yeah. So then I'm writing it in the basis of the vector spherical harmonics. So it's the basis times some function. It's just a decomposition of any function of tr theta phi in a very generic way in terms of the basis of that space, which has symmetry, a spherical symmetry.
Achha, this is just decomposition.
Exactly. It's like if I just did a decomposition of a vector into something like this. So I'm just making a decomposition on the basis, which are the vector spherical harmonics. So I can always do that, and I'm getting multiplied by some coefficients, which I don't know, but depend on Lm, etc. It's like, for example, if I had spherical harmonics, so I'm saying that any function which is square integrable, I can write it as some function of tr times the spherical harmonics. Again, I don't specify at all what it is. It's just that I can always do that for a squared integrable function, actually. Okay, so we do these decompositions, etc. And then we end with the vector perturbations, which do have this form. You do the same calculation for the scalar perturbations. It's a bit more complicated because we are not going to have 3 free functions, but 7. So you will get one term here, etc., etc. So you will fill all this. you get something a bit bigger, but it's not more complicated than you have it in the notes. Now, we can add a simplification, actually. A very important simplification, because otherwise this is a bit too complicated. The thing is the following, is that we have a symmetry by rotation. So the spherical harmonics, remember how a spherical harmonics come. It comes like this, as a Legendre function times an exponential im phi. This is how it comes, the spherical harmonic. Now the thing is the following, because you don't have any preferred axis in your space-time, you can calculate the perturbations only for m equal to 0. Imagine that you calculate the perturbations for m equal to 0. Then if you want to have the other perturbations, you just have to make a rotation of it. And then you get the other type of perturbations. So we say that we are looking just to axisymmetric perturbations. That is a big simplification, which comes just because you don't have any axis which is privileged. So you can take any, imagine that you have a perturbation which is a bit more complicated. You can always go back to m equal to 0, do the calculations, and at the end you make the rotations that you want and go back to the calculation you wanted originally. So we can calculate everything because there is no privileged direction, because it is a spherically symmetric problem. You can always work with m equal to 0. You can find the full argument in the book by Chandrasekhar in the section of perturbations. So if m is equal to 0, all my spherical harmonics will be just theta dependent. The phi dependence will just go away, actually. So what it means that this goes, there is no derivative with respect to phi, there is no derivative with respect to phi, there is no derivative with respect to phi, etc. And actually my perturbation becomes much simpler. So it simplifies a lot the calculations. The spherical harmonic becomes just the Legendre actually polynomial here. Okay? So you have always to do that if you want to simplify a bit your calculations. And doing this, then you get a quite simple kind of perturbation which has this form. So for vector perturbations, what you get is the following. H mu nu is equal to 0, 0, 0, 0. You get also a 0 here, another here, as we said, we kill it. You get just H0. H0, it's a function of t and r, sine theta. The derivative with respect to theta of the Legendre polynomial. The function H1. And then you have 0, 0, 0 here. And this one, you have this, which is also a function of t and r, all of them. And you have a cos theta, d theta, minus sine theta, d theta squared, pl. And, sorry, this is not 0. This is a symmetric object, so no, this is 0. This is not, this is not, this is not. And there is 0 here. Okay. So this is our perturbation actually for vectors. So we wrote, just thanks to the symmetries, etc., how the perturbation should look like. So these are going to, once you understand it, how you reach this point, then you don't have to do that all the time. You just say, I'm looking for vector perturbations. That is my perturbation, in the sense that for any space-time, it doesn't depend on the theory of gravity. If you do GR, modify gravity, whatever you do, it will be always the same structure. We didn't use at all the theory of gravity. So you will say that G mu, your metric, is your background metric, whatever it is. It can be Schwarzschild, it can be any other space-time, plus H mu, which is going to be an epsilon, something small, which has this form. You plug this back, you plug this in your equations, and you expand at the first order. These are the quantities that you know, and you will get some differential equations for H0, H1, and H2. And you will try to solve them and find how these perturbations are actually evolving. So that is the picture, the global picture on how to do it. But actually, we can simplify it a bit more. I don't know if you have questions at this point. So then you have an additional simplification, which is the same thing that we did in cosmology, the gauge freedom, actually. You can always change the system of coordinates, and actually you can simplify your problem. So what is happening is that the same way, if you remember in cosmology, we had, for example, for scalar perturbations, we had 4 scalars. We did a change of coordinates. We went to a specific observer, and for that specific observer, we could kill 2 scalars. So we were left with only 2 scalars. Here it's going to be the same thing. You do a change of coordinates in the sense that you say, okay, I will consider that I had a system of coordinates x mu. I will change it into some x mu plus xi mu, some small transformation. It can be a rotation, a translation, a boost, whatever transformation we can think of. You do that transformation, then some of the terms might actually disappear. And actually, you will find it in the notes, you can prove that then there is only one possibility. Let me write just the transformation for you to see how it works. There is some transformation of the coordinates, and what you get is that h0 transforms more or less like this. This is the time derivative h1 Okay, so this is going to be the transformations in the sense that you have a coordinate system. You change the coordinate system. These functions are changing, of course. They always change. They are not invariant. So when you change your coordinate system, so they change in this way, okay? And this is the transformation. Then you say, okay, I can fix my transformation here in such a way that I kill H2. That is possible. I can always kill H2. The others, if I kill them, I don't kill them completely because it's a differential equation for xi, means that I will not fix completely my gauge. And this is called the Reggie-Wheeler gauge. So it's a particular actual transformation which kills the H2. And as you can see, the H2 was one of the most complicated terms. So I will just kill it. And that is now my perturbation h mu nu. So I have just 2 functions which are free now, h0 and h1. And I can work with that, and that is my perturbations for my metric for vector perturbations. And you can do the same thing for scalar perturbations, okay? So again, once you understand that, you can really start already from that. That is the most general perturbation for any theory of gravity as soon as you work in 4 dimensions. In 5, it will be a bit different. As soon as you work in 4 dimensions and with spherically symmetric background solution, then you write it in this way. So now it's easy. You just take your equation, Einstein equation, r mu nu equal to 0, and you expand that at the first order. So you write this in the sense that, okay, you have a metric, which is this. From this, you can calculate the Christoffel symbols, which are going to be something at the linear order in H. If there are any terms which are second order, you just kill them. So you go at linear order of perturbation, you calculate your Riemann tensor, etc. You get the Ricci, and you have to fulfill this condition, which is the GR equation. Now we use the theory of gravity. Now the equation that you will have depend on the theory you have. So if you work in modified gravity, that equation will be different, and you will get another set of equations, of course. So then you write the equations. Some equations are going to be completely trivial. For example, if you write the equation R00, the R00 gives nothing. in the sense that there will be no h dependence at all actually at the linear order. They just cancel each other and in the end you get nothing. So there are three actually terms which are going to bring something interesting, which are the R23, R13 and one R03. Each one, you write the equation equal to 0. You get something. Then you get an equation for H0. You get an equation for H1. So there are two partial differential equations which are coupled, which are a bit complicated. But the very interesting thing is that this is what the work by Reggie and Wheeler, which developed all the theory about it, is that if you redefine this function to be some r times some function tr divided by our metric, if you do this redefinition, actually, you can simplify a bit the equations, etc. And at the end, you will get a very simple equation, which is like a Schrödinger type of equation. And the r star is what is called the tortoise coordinate, and it is just that it's just related to r actually. R star is just r minus 2m log of r divided by 2m minus 1. Okay. And there is a plus here. So. Questions so far? So when you work on these perturbations, the main thing is always to reach an equation like that. Most of the time they call it the master equation for the perturbations. So what does it mean? Imagine that you have this equation at the end of all this process. So you have an equation for Q. You solve Q. Once you solve Q, you have H1, of course. H1 is just this. And from the other equation, you get H0. H0 depends on H1. This is the relation you can find in this process. So at the end, there is only one function which is really independent. H0 and H1 are not independent. They depend on each other. So actually, there is only one variable which is independent. Let's call it Q. So you solve that. Once you have Q, you have H1. Once you have H1, you replace it, you get H0 actually. Okay? So there is actually only one degree of freedom. For scalar perturbations, it's going to be the same. You have 7 functions. First, you use your gauge freedom. You cancel 3 of them. You are left with 4. With these 4 functions, you can work it out, all these equations, and at the end, you will find only one function which is independent, some other Q. And if you get that solution, you reconstruct all the other perturbations. So at the end, you have only 2 functions, 2Q, which are really independent, which are the 2 degrees of freedom that we have in gravity. So these are going to be one type of perturbation, and we will have the other type of perturbations. So the main thing after is just to calculate that. But as you can see, this is like a wave type of equation, and it's good. This is why we call it gravitational waves. It's a wave type of equation with here a coefficient which is 1. If it is 1, it means that the speed of propagation of this type of theories is the speed of light for these gravitational waves. If you work in modified gravity, you will find something here, some coefficient. That coefficient will be the speed of propagation of these gravitational waves. So you take any theory, you do this calculation, you put this metric in your equation here, you use Mathematica, for example, expand at the first order, you simplify a bit things, etc., and at the end you get an equation of this form, and it tells you what is the speed of propagation of these waves in that theory. Okay, so this is one thing, to have a knowledge of the speed of propagation of the gravitational waves. But now what we want to know is the stability, because this is what I was talking about before. Stability is that we want to know if that perturbation, remember that Q is just H1. So we want to know if we take a Q of this form times some function of R. Did I take plus or minus? I took minus. So we have a Q which has this form actually, and imagine that the omega here, the imaginary part, because omega can be real or imaginary. Imagine the imaginary part is positive. Then you have a global coefficient here which is positive times t. So when t grows, the exponential will diverge. Your perturbation will grow with time. If the imaginary part of omega is negative, so when imaginary part of omega is positive, then this grows with time, and the black hole, you say it's unstable. If the imaginary part of omega is negative, then it is stable. So the sign of the imaginary part of it will tell you if it is stable or not, because if the imaginary part is negative, then you get minus t, and when time grows, that exponential will decay and q will go to 0. So what does it mean is that you have a perturbation initially, that perturbation will just go away and it will become 0, so your black hole is stable. In the other case, your perturbation starts small, but actually it will grow with time and it will become bigger and bigger and bigger, and at the end your black hole is completely unstable. So the stability of the black hole will be just linked to a very simple thing, asking if this frequency here, which are the frequencies of the gravitational waves, if they are positive or negative, the imaginary part. Now let me just comment about something. If you take in classical physics, in mechanics, so just to link it to something that you might know, you might have did this course in undergraduate, you take classical mechanics and you take something like this. You take a first spring with a coefficient k, you have some mass m1, you get a second one, for example, you have a mass m2, etc. Let's suppose that we have only 2. I'm sure that you have all studied this problem. So this can have oscillation. It can oscillate in these two masses in a bit complicated way, etc. you can have. And yeah, I don't even know why I put a mass here. It will be useless. So we have actually I will put a mass, but so if I'm looking to these two masses here, they can move like this, they can go in the same direction, they have different modes, different oscillations. What we know in classical mechanics is that actually there are some particular modes which are called the normal modes. The normal modes, in this case, we will have actually two normal modes. One which is this oscillation, like this. The other one is like this, in opposite. Now, any type of oscillation can be written as a combination of these two modes. These are kind of fundamental modes of your theory. These are known as normal modes, and any of them can be decomposed into these normal modes. So mathematically, you would say that the normal modes form a basis of all the frequencies. Here, for a black hole, we have exactly the same situation. We have actually different modes, different frequencies, and actually any gravitational wave which might have any kind of frequency, it can be a very strange oscillation. At the end, you can decompose it into some very fundamental frequencies, which are these normal modes, which are called here quasi-normal modes. They are not exactly normal modes. Why? The reason is that you have an imaginary part. It's not that you just have a real part. You have an imaginary part in these frequencies. Means that your exponential, it becomes actually, there is a real part which produces oscillation, and then there is actually an imaginary part which makes that actually this decays with time. So you get something like that, so actually it decays with time. So while here you don't have any kind of form of dissipation. Why here it decays with time or it grows with time, depending on the sign of it, you have a dissipation because actually the structure of the space-time emits gravitational waves. Some gravitational waves, they enter the horizon, we lose them. Some of them, they go to infinity, we lose them. So in that sense, we say that the system is dissipative. It will lose some energy. And that is the decay that we have here, the stability, that the black hole first it is perturbed and starts emitting a lot of gravitational waves. Some they enter the black hole, some they go to infinity. So we have a form of dissipation and we lose part of the system. This is why these frequencies, they are not just real, there is an imaginary part, which means that they are just quasi-normal modes and not exactly normal modes. We are losing part of them because we have dissipation. So
it means that if you take a perturbation in original metric and do all this mathematics and then you come up with this equation of Q. And it means that Q is the governing whole scenario.
Yes.
And then the equation, this is a wave type equation, so solution is like this. Q e raised to minus omega t q pi r, no?
Yes, yes. Some function of r that we will still have to define here.
How do you pi r means? But it's not that much important.
No. It is fundamental. Actually, so let me just rewrite. I have this equation, and I replace it here. Okay. So the double derivative with respect to time will bring me some omega m squared. So I'm just going to end with an equation, which is the So this is the equation. Yeah, this is the equation that we are going to have. I'm just replacing here. So the exponential will give me here a minus omega squared times phi. And so minus. Between them there will be a plus sign. And the potential here which comes. So then I reduce it to actually a Schrodinger type of equation. And this kind of system I can solve. So I can solve this problem with some boundary condition that I have to specify now. And if I can solve it, then I have phi, then I have my perturbation, then I have everything else, actually. Then I have the full solution of the perturbation. But actually, one thing is that it's like, in some sense, in quantum mechanics.
Yeah.
Imagine that we have the Schrodinger equation, and we impose some boundary conditions. What we get a system which is quantized. We get actually energy which is become discrete and not a continuum values. Here, we are going to impose some boundary conditions, one on the horizon, one at infinity. That is like our box, actually. Imposing these conditions, actually, will fix actually a condition on omega. We cannot have any frequency which solves this specific problem. If I choose omega equal to 3, for example, let's say it's a free parameter, it's just whatever frequency we can imagine. I take omega equal to 3. The potential here I didn't say, but it depends on the model we take. For GR, let me just write it in order to be complete here. just to show that it's just coming from the metric itself. You do the full calculation, and you get something like that. Okay, so this is for vector perturbations. These are the modes that we had in the spherical harmonics, the y, l, m, theta, phi. When we start making derivatives, etc., they appear. So we have different modes, actually. So this is the potential we will get. Okay, so the potential is fixed. This is for Schwarzschild. The potential is fixed. Everything is fixed at the time. We can solve this equation. Imagine I would say, okay, I would like to study all the modes in my theory, and I will study the mode L equal to 2. Okay, fine. L equal to 2 here. I take a mass m equal to 1. It's 1 solar mass, for example. So the potential is completely fixed. I put it here, and I try to solve this differential equation. Now I have here this parameter, which is the frequency. Initially, I would say, okay, I fix it as I wish. I take omega is equal to 4, and I solve it. But actually, this will not be exactly the boundary conditions I want. At the level of the horizon and at infinity, it might give me something else. It will give me a solution for sure, but not exactly the boundary conditions I want. Only very, very specific frequencies are going to solve exactly this equation with the boundary conditions I want. So then we get just few frequencies, not few, they are infinite, but they are discretized. There are just some value of them, and these are going to be the frequencies, the fundamental frequencies of my black hole, which is oscillating, what we call the quasi-normal modes. It's not any kind of frequency. We cannot have any type of frequency, but just these very particular ones. So let me just say, what are these boundary conditions? To make it more clear, actually. So the boundary conditions are the following. We have a black hole, we have the horizon, and we are solving our equation from the horizon to infinity. This is the range where we are solving our equations. I'm not entering the black hole, etc. I'm outside the black hole, so I'm interested only on what's happening outside. So the thing is that I have to impose two conditions, one at the level of the horizon, one at infinity. Now, at the level of the horizon, I look to the equation how it will look like. When I am at the horizon, r is equal to 2m, that becomes 0. So at the level of the horizon, the potential is 0, actually. This is at the level of the horizon. So the potential goes away. So I have a very simple equation near the horizon. I have an equation which is let me just write it like this, plus omega squared phi equal to 0. Okay, so this is the equation that I have near the horizon. So if I'm coming very close to it, I have this equation. Now this equation has two solutions, which are exponential plus or minus I omega r. And remember the sign, the q. The q is exponential minus I omega t times phi. So it will be exponential minus omega t plus or minus r. So these are the two solutions of q near the horizon. The thing is that what are these solutions? They are just actually a wave, which is an ingoing wave or an outgoing wave. So these two solutions are just either a wave which goes like this or a wave which goes like that. This is this exponential. The t minus r is a wave which is going out. The t plus r is a wave which is going in. So they are just plane waves, one going in, one going out. The point is, because now that is just mathematics. I'm looking near the horizon, I'm getting two solutions, and the two solutions are plane waves, one going out, one going in. Now I put physics. I say from a physical point of view, nothing should come out from the black hole. So that solution should not exist. I should have only actually waves which are going in. So between these two, I should impose that my condition here of the solution should be that the one with this sign, which means that phi is exponential plus I omega r. So this is going to be actually the condition that I impose on the horizon actually, at the level of the horizon. I want to impose something which is physical. So I impose this condition that I solve my differential equation, but with this condition here. At the same time, I can do the same trick at infinity. If I go to infinity, the potential becomes again 0. So it becomes again 0, the potential goes, I have exactly the same solution. So I have either a wave, plane wave going, ingoing, or outgoing. Again, I impose a condition. I say that there is no, what it means, something coming from infinity. So I will consider only that solution, which is going to be the exponential minus I omega r. So these are now going to be my two boundary conditions that I will fix on this particular equation and solve it. And with this, I'm going to get just some very specific modes here, some specific frequencies. We can do it either numerically. It's very complicated numerically to solve this equation with this condition, because remember that here you get always two solutions. But the point is, if this coefficient is extremely, extremely small, you might not see it numerically. Actually, there is numerically, for example, something coming out, but you don't see it. You have to impose strictly that this one is 0. So numerically, it's tough, but you can do it. Otherwise, there are some analytical approximation to this type of equations. There are different methods which have been developed in the literature, and you can actually look at them if you want to calculate these frequencies, which are known as the quasi-normal modes. So these frequencies should depend only on the very parameters of the theory, which means in our case the mass, for example. If you have some theory which is different, like with a scalar field, you will find frequencies which are different than the Schwarzschild solution in general relativity. So that will be very specific to each theory, and this will be, with time, hopefully be able to really observe that or not. Now, for the moment, people are observing these gravitational waves with the precision we have, which is not very, very good precision. It's consistent with GR. So we cannot say anything so far. With more precision, maybe we will detect something, maybe we will detect nothing. But this time will tell us. But that is the idea on how to impose that. Just to conclude, the last comment about, I said that stability means that the imaginary part of that frequency that you calculate should be negative. That means stability. You will find in the notes the proof that if this is negative, it is equivalent, not equivalent. It implies, almost exactly it's in this way, that if that potential here is positive, in the sense that when you calculate your theory and you get this potential, if this potential is positive, then you have automatically stability. If the potential is negative, then you might have stability, you might not have stability, then you have to go to some more involved mathematics, etc. I will skip that. For the people who want, I can send some notes about what is called the S deformation. But otherwise, if you get at the end a potential which is positive, then you can say directly it's stable. You don't have to calculate it, it's star, because people they already did the job for that. And if you look to this potential here, what form it has this very specific form. You see that it depends on two parameters. Let me fix the mass to anything. We can just normalize actually the R. And I will take different values of L. This is, I will say that this is the horizon. And this is at infinity. So it does something like this. This is for L equal to 1, for example. Then you get this for L equal to 2. Then you get something like that for L equal to 3, etc. So this is the potential that you have here. And you see that for any L, you will always have positive. So it means that the solution is stable, and that was what was proved quite some time ago, that Schwarzschild spacetime actually is stable under linear perturbations. We are not looking to nonlinearities. We are not looking to the full space-time where two black holes are colliding. It's just very small perturbations. I take the Schwarzschild space-time. I produce a very small perturbation. That perturbation will decay, will go away, just because it's emitting some gravitational waves. Some of them, they go in. Some of them, they go to infinity. And at the end, the black hole remains the same, and it will be stable. And that is just because that potential here is positive, actually. Questions, if you have.
Is it question is valid for the all type of black holes?
Which one? This one?
I am especially talking about rotating black holes.
Yes. No, it will be different. It will be different. This formalism is for non-rotating black holes. Yes. For rotating black holes, it took quite some time actually to do the calculations, to find the way to make the decomposition of all functions, to separate actually even the separation we did in terms of scalar, vector, etc. That you separate that in some simple equations. That took quite some time for rotating black holes to do it. In this case, how it is? What's the name of this South African who did it? No, there is a guy. He's from South Africa originally, and he's in the US since quite some time. He's the one who developed mostly the theory of perturbations for rotating black holes. Forgot his name. Remember his name? No. I will tell you just after. It will come back to me.
So, just I would like to know, that means you are taking a Schwarzschild black hole, you are taking some perturbation.
Yes.
And finally, with the help of this Q equation or phi equation, you are proving that it will get stable.
Yes.
That you are proving.
Yes.
But what is the main motivation, or what you can say objective to consider perturbation?
Yeah, there are two things. That was the motivations I was giving at the beginning. One is to know about stability, because it's important for modified gravity, for example, or even for GR. Let me just skip with GR.
Yeah.
Let's go just with GR. I have a star which is collapsing, and that star will form, we suppose, a Schwarzschild black hole, some black hole. If I can prove that that black hole is not stable, imagine that it's not stable, that I know that that star is not going to Schwarzschild, because Schwarzschild is unstable. So if it goes to Schwarzschild, then it will get destabilized, and it will move to something else, to another structure. So if I want to know if the end of all the collapse is Schwarzschild, is that particular black hole, I have to know if that solution is stable. If it is not stable, the star is collapsing. Maybe during the transition it will be a bit Schwarzschild, and then it will get destabilized and move on to something else. So it's important to know if the end state of this collapse is going to be Schwarzschild or not, and this is stability which is telling us that. The other thing is to test general relativity. As I was saying at the beginning, these perturbations at the very end of the black hole. So we have a black hole which can be very deformed during the collapse of two black holes, very complicated shape, but at the end we get something very close to Schwarzschild. And that is where we use these perturbations. Now these frequencies here, they depend only on the parameters of your black hole. Means for us just the mass. You give the mass you get these frequencies. So imagine that we have proved with the calculations what are these frequencies, etc. Imagine that you observe and you find a complete different structures. You find that this parameter does not depend only on the mass, but on some other parameters. It should depend, in a generic thing, it should depend on the mass and the angular momentum also, because they are all rotating, of course. So if you have you observe some signal which does not depend only on these two parameters, but it depends on some other parameters that you didn't know, then you would know that actually GI is not a real theory, that there is some other theory which brings with it some additional parameters which are not just the mass and the angular momentum. For example, if you have a scalar field, that will give some additional structure, actually, which is not just mass and angular momentum, but what we call additional charges, actually, which are going to some additional parameters.
And suppose we end up with unstable.
Yeah.
Suppose.
Yes.
Then can we say that then the black hole will turn into a naked singularity?
Yes. Or a naked singularity or any other structure. Then we will have to make a full simulation and see to what it will evolve.
It will lead to.
Yes. But at least at the linear order, I cannot say about the full evolution, but I can just say, okay, this will be unstable, so it cannot remain there. Because a small perturbation will just transform it into something else. So then, yeah, that solution will not be, we will have to find something else. This is what's happening in higher dimensions.
Yeah.
In higher dimensions, there was, for example, something which is not a black hole. It's a string, a black string. It means that it has a line, singularity, it's not a point. And we have a horizon, which is like a cylinder like this. So it's like a black hole, but with an extra dimension. So it's called a black string. This has an instability. And this we can prove it at the linear order. So we know that at the end we will not get this. Now what it will be at the end, you need to do a simulation. And people found that actually it gets separated into a set of black holes like this. And you get like a line of different black holes. But so at the linear order, you just understand that the first picture is wrong. Now, what it will be, then you need to do the full evolution actually to get it.